Hey everyone, E.T. here, and we're back with WYSTEM, and I am super excited because tonight we are kicking off the final week, which is crazy to believe that we've already gone through 3 weeks. We've learned about science, we've learned about technology. Last week we learned about engineering and 3D printing, and then this week is all about mathematics, and we're going to continue learning about coding and 3D printing with a very special guest this week, Lars Kotthoff. He is a computer science professor at the University of Wyoming, and he's going to show us even more cool things. So if tonight's your first night, don't worry, because all of the other sessions that we've done 2 every week, are available for you to watch at any time on YouTube. So you can go back, rewatch them, because one of the cool things that you guys can do for this WYSTEM project is if you are a Wyoming student in a Wyoming school, you can win a 3D printer, which you probably saw if you joined us last week. They're super awesome. We're going to learn more about them. So how do you win this 3D printer? Well, each week, there is a hidden code word. So it could be on the first video, part 1. It could be on part 2. It's just going to show up in this little area of the screen very briefly. Make sure you write them down because we've already had 3 keywords, code words that have shown up. And then this week, either tonight or on Thursday, when we do part 2 of mathematics, we might show the 4th and final code word. And then when I see you guys again on Thursday, there'll be a form where if you caught all those code words, you can enter them in and select, hit the submit button, and you'll be able to be entered into a drawing that we'll do on Friday to win a 3D printer for your school. So we're really excited about that, so keep your eyes out for those code words. If you haven't caught them all, go back to the YouTube videos and watch them again. So definitely want to thank all of our participants in the last 3 weeks. We've had some amazing people, and this week is no exception. So we're really excited to welcome Lars to talk to us about math and science and 3D printing and a bunch of other cool things. And then just a heads up, we're going to probably have a few technical difficulties this evening with some of the videos that Lars has. So just kind of bear with us as we transition our audio and our video settings so that hopefully you can hear them. If for some reason you can't hear the videos, we will include the links in the description of this video so that you can just click on those and watch them at your own leisure. But we're going to try to do our best. So without further ado, I would very much like to welcome our mathematics kind of champion and leader, Lars Kotthoff. Take it away.
Thanks, E.T. Hey, everybody. We're going to talk about math, but don't worry, we're not going to get too technical here. There's not a whole lot of math we're going to talk about. It's really about how do we tie everything that you've heard about so far together. You've heard about science, and you've heard about technology, and you've heard about engineering, in particular 3D printing, maps, and mapping, and things like that. What's behind all of this? Turns out there's a lot of math that you kind of need to know, unfortunately, if you want to do all of this. And we will have a look at a tiny little bit of that. That should hopefully be fun, and that will help you do your own very cool projects. So let's get started. Well, first, I want to talk about the thing that ties both mapping, which you've heard about the week before last, and 3D printing, which you've heard about last week, together. And that is really that we need some way of representing stuff that happens in space. This could be 2-dimensional space, something flat on a map, as you've seen with Teal for the technology week. That could be something in 3D space, so something you can 3D print, a 3D model, what you've done last week with Tyler. How do we actually represent this in a way such that a computer can understand it? Because that's what's behind all of this. You've seen Teal show you maps on a computer, and you have seen Tyler show you 3D modeling on a computer. And then you saw these 3D printers, which are also kind of like computers, which then actually printed the thing. How do we actually do this? Turns out behind all of this, there's one very simple thing that you probably already know: coordinate systems. That's some way of allowing us to describe in a mathematical notation what's happening, where are points, how are these points connected, all of these kinds of things. And the good thing about coordinate systems is that it allows us to do a lot of stuff, and it allows us to then take this stuff and apply it in other contexts. And I'm sure that you probably have heard about coordinate systems already. If you're not entirely sure what this is, we're going to have a look at a quick refresher video And this is Q first set of technical difficulties, ET first video.
To plot the ordered pair, 2, 1, go right 2, jump up 1, and it's done. To plot the coordinates 7, 10, go right 7, up 10, mark it with your pen.
On the x-axis,
Count to the right.
on the y-axis,
Count from the ground. That's how a coordinates point is found.
To plot the ordered pair, 3, 5, go right 3, up 5, to where you arrive. To plot the coordinates 10, 7, go right 10, up 7, we did it again.
on the x-axis,
Count to the
on the
right.
y-axis,
Count from the ground. That's how a coordinates point is found.
To plot the coordinates 9, 4, up right 9, up 4. Now one more with the ordered pair. 0, 4, remain at the origin, count 4 from the floor.
on the x-axis,
Count to the
on the
right.
y-axis,
Count from the ground. That's how a coordinates point is found.
the coordinates are kinda like clues, telling you where to plot the x and y values. And when you see them on a questionnaire, they can be called coordinates or an ordered pair. We plot x first, then y, that's the order. Always starting from the bottom left-hand corner. That's the place that we begin. At 0, 0, call the origin. On the x-axis,
Count to the
on the
right.
y-axis,
Count from the ground. That's how a coordinates point is found.
Little thing I want to mention here, we talked about the origin in the video, so this point that's 0, 0, and that's actually very special because 0, even though it seems very straightforward, is not really. In particular, you've probably heard of the Romans. They built large temples and cities and statues and things like that. They didn't even have a 0. They didn't invent the concept of 0. They didn't have it. They had all kinds of other numbers. If you've seen them, they're these weird letters. They didn't have the numbers that we use today, but they didn't have 0. So this is very special, and it's a kind of weird thing if you think about it, because it expresses that there's nothing. Why do you want to express that there's nothing? Doesn't really make sense, right? If there's nothing, why would you talk about it? Except in cases like this, for example, when we're talking about coordinate systems, it totally makes sense, and it's totally necessary because we need to tell where does everything start? Starts at 0, and then you go to the right, and then you go up. And if you go in a third dimension, you go in this and in that direction as well. Now, there are other people who did have the 0 pretty early on, and this is where I get to use my first prop here. This is called the Leiden plaque, and this is an artifact by the Maya civilization in Central America. I'm showing you this because this is one of the first known artifacts where the 0 was mentioned. If I turn this around, so on the front here, we have big guy, some king. We don't know his name, unfortunately. He lived about 1,500 years ago. And on the back, we have a bunch of writing, not as we know it, but as the Maya did it. And if you look down here in one of the corners, you can see a 0, and this is the first time that the 0 was used by the Maya, as far as we know. Yes, It doesn't look like our zero. It looks completely different, but hey, it was 1,500 years ago. So a lot of time has passed since then. This is, of course, a replica and not the original. If you want to see the original, you can go to the Netherlands, to the city of Leiden, which this is named after, and you can see it in a museum there. Or maybe this is the original and I had a replica made, went to the museum and swapped them. We will never know. Let me put this away in a safe place. There we go. Okay, so now you already know more than all the Romans that ever lived, because that you know that there's this special thing, zero, that means that there's nothing, or that there's the origin of our coordinate system. Okay, so what can we do when we have a coordinate system? We can describe 3D models, all the things that you have seen last week, and we can describe maps, all the things that you have seen the week before. We can point to particular points in a coordinate system and we can say that, oh, this city is there, I live there. Or this point is where the eye of the cat is, or something along those lines. And this then allows us to describe a 3D model, for example, in particular in a way that we can tell a computer about it, and then give it through a 3D printer, which might have a motherboard, a chip like this guy here. So then there's a signal coming in somewhere here that says, okay, move to point 3,2 and put some plastic there. Oop, this is falling apart. Okay, it's only a spare part. Don't worry, the 3D printer is fine. Now, where was I? Oh, yes. So the model says move to this particular point and then put some plastic there so that we can build a 3D model. And this chip then translates this into, okay, I need to move this far in the x-axis. I need to move that far in the y-axis. And the z-axis, I need to move that far. Translates that into commands for the motors, for the stepper motors of the 3D printer, which move the actual printhead that you have seen last week to that particular position, and then start pumping some plastic, some hot plastic through the nozzle at that particular point. What else can we do with this? Well, maps I've already mentioned. Here's something else that you can do. This is Wyoming, even though you might not recognize it. This is 3D printed. This is a relief of a topographic map of Wyoming described in exactly the same way. We have X and Y, and in this case also Z coordinates that tell us how high we want to go. This is obviously not original size because I don't have a 3D printer that's big enough to print all of Wyoming, but you can kind of, hang on, let me see which way around this is. You can kind of see it here. We've got Cheyenne somewhere down here, and then here we have Yellowstone National Park and the Grand Tetons, and you can just print this. This is a model with some mathematics behind it. It's a computer file that I can give to one of my 3D printers, and then off we go, and I can print this. What else can we do with this? Well, this guy that I've already shown you when we kicked this off, another 3D model. And it's really described in pretty much the way that I've told you, that here's a coordinate, and this is some number, for example, 342 and 7, and there's a little bit of plastic there, or there's a little bit of material there. I don't have to print this in plastic, obviously, I just did that. I could print it in metal or something else as well. And this way I can describe this entire model. For each point that is on it, I can say this is the coordinate of this point. And then there's a bunch of coordinates where there's nothing, and I simply don't describe those. I say, well, there's nothing there, so there's no need to describe them. I will just have the points that are on the actual model. Now, what is this actually? This looks kind of weird, right? This is what's called a Klein bottle. And you can think of this as having a normal bottle where you take the neck and then you kind of turn it on itself and into the bottle so that it comes back out at the bottom again. Now, don't try this at home because you will break the bottle and your parents will probably get mad at you. But this is a great example of something that we can 3D print, because otherwise it's kind of hard to make these, and you need specialized equipment. You can't just take a bottle and kind of, turn it in this way. However, some people have actually done this, including somebody who has much cooler hair than I have, and he's going to tell you more about Klein bottles and show you his collection. Cue second video, ET, please.
So I call around glass companies, glass shops. How much would it cost to make like a bunch of them? I want the price to be low enough that I can sell them. Turns out making one or two isn't going to do it. Making 10 or 20 isn't going to do it. I have to have like 1,000 made. Come on over, check this out. Under my house is my little forklift robot to go pick Klein bottles from stock. Tilt the thing. If you look carefully at it, let's see if I can actually show this. I mean, this is just homebrew. This is only incidental. This is not Klein bottles. This is how to run a warehouse, really. This is the lift mechanism from a car window, from an old Pontiac car. So I went to a junkyard, got a window tilt. Everything's made from junk. The up-down, that's an old electric drill that I got for $5. The wheels, you know, they're little motors, drive the wheels around. Let's tilt this up, lift it. So here's a box of, oh, hey. And yes, there are Klein bottles in here. And indeed, this is a box of throwaway Klein bottles, things that have flaws on them, but I don't care about that. The main thing is there are lots and lots of bottles. It's the footprint of my house. I mean, let's see. Hey, go back. Let's drop this off. From here on out, you're going to have to look at a TV camera because you have to appreciate that there's lots of bottles. And heading over to where I store bottles under my house. Let's see, there are lots and lots of baby Klein bottles in boxes under my house. And lots of medium-sized Klein bottles under my house. The reason for having so many bottles isn't, oh, I gotta have, in case somebody orders a lot. It's so that in manufacturing a lot of them, I can keep the cost low enough that I can sell them. Turns out that small production runs are real expensive. So if I can just have one production run, save enough bottles for the next 10 years. So notice now there's both Brady and Cliff both are being seen by the rear camera of my little forklift robot.
Hang on.
Behind you is a cat.
Okay. Hang on a sec.
Sure. No, he's going out. Cat's gone. Don't worry about it.
That's all right. I've got the shot now if you come around towards me.
Goodbye.
Have you got something you'd like to sell online? Maybe.
Thanks, E.T. So there you go. You can even make money doing this stuff, knowing math and everything. So let's have a look at what these coordinate systems actually look like for this particular model. And for that, I will share my screen. This will take a second or two. Now, if you haven't noticed already, and I'm sure you have, as I said, I'm a computer scientist, and that means that every talk I give and everything I do has to have the fundamental laws of nature, like gravity or things like that. Okay, that said, here's a Klein bottle, and here's my coordinate system that I have drawn here. This is a 3D modeling program similar to the one that you had a look at last week. That's going to do slightly different stuff, but in the end, you get 3D models out of it. And I've drawn in here, you can see the one axis there, another axis there, and Z going off in that direction. And now I can move this around, and I can look at it, and I can take the coordinates for individual points. Like, for example, up here, this is somewhere around 6 for Z and something else for X and Y. And then I can say that, yeah, okay, there's this kind of curve going through this, and we take the top and we turn it back onto itself. We have the hole at the bottom there that you can see. Okay, great. Now I have the description of this in my coordinate system, and I can do all kinds of cool stuff with it. For example, 3D print it. But this is not actually everything I can do with a coordinate system, because I can now transform the coordinate system and use that to transform the object that I'm working with. For example, I can rotate this. Let me show you here. There we go. We just flipped everything around. And that is very simple. I don't need to do that for every individual point in this klein bottle here, but I just do this for the coordinate system. I take my description of the object that I'm interested in, and I apply a transformation, a so-called transformation, in this case, a rotation, to the coordinate system. Okay, that's really cool. Let's take this back. Here it is. What else can we do? Well, we can scale all of this. If I don't want to print it that large, maybe I want to print it smaller, like this guy here. Okay, that's also pretty cool. I can do some crazy stuff, though. Let me make that big again. There we go. I can scale it in only one dimension for only one of the axes that we have. So here I've scaled it for Z. As you can see, this is kind of all squished down now, and now the model looks completely different. This is something, again, that I can do very easily by transforming the coordinate system. I don't have to go in and say, okay, now this point has kind of moved down, and then this point here has kind of moved down as well. Do that for every individual point. Sounds like a lot of work, right? We don't want to do that. We don't want to do that every time we're transforming something like this guy here. So instead, we're transforming the entire coordinate system. Okay, let me unsquish it again. There we go. That was easy. I can also squish it in another direction here. So now it kind of looks like it got hit with a car and squished against a wall. I can make it more squishy, like this guy here. This is now almost flat. I can make it less squishy, like this guy here. This kind of looks like the original, but not quite. So let's unsquish it again. Here's our original Klein bottle again. And all of these things I can do very easily. I can do other things. For example, I can move everything a little bit. There, not sure if you saw that. Let me undo that, go back. Everything shifted a tiny little bit. There we go. This can be useful if you have multiple objects. So maybe I have a second bottle here, or I have something else that I want to 3D print, and then I want to move one of these objects around. I don't want to go in for every individual point and say that, okay, now move this point, now move that point, now move that point. Sounds like a lot of work, right? We really don't want to do that. So again, instead, we shift the entire coordinate system. And this is actually what I've been doing all along. So let me put the coordinate system back here, and let me remove the one that I put in manually. And then we can see that what you saw in the beginning, these numbers that I put in from 0 to 10, are not actually true. This goes up to 1,000 here and minus 1,000 there. And these are arbitrary units. They don't really mean anything. They only mean something once we start to 3D print it, for example, or put it on a map where we have a reference that tells us what exactly one unit in this coordinate system means. Here, they're really just a bunch of numbers. And as I just showed you, we can manipulate and change these numbers arbitrarily. We can squish one dimension. We can kind of stretch it in another dimension. We can rotate it. Let me rotate it some more. For example, like this here. Whoops, now it's gone down a little bit. All of this happens just through transformations of the coordinate system. I don't need to go in and change the representation of the bottle itself. Okay, now let me show you some other cool stuff that You can, again, 3D print, and that I have 3D printed here. And there I'm back. Because as it turns out, we can use math not only to describe coordinate systems and what's in them, for example, this bottle here, but we can also use math to describe the actual objects. Let me show you an example. This one I have shown you before. These are two gears that are connected to each other, and they're kind of the same, right? So if I want to print these together, I simply take one gear and then I say, okay, the second gear is exactly the same, except it's rotated. So again, a transformation of the coordinate system, as I've just shown you on the screen, allows me to do this very quickly. I don't have to copy all the points here and then kind of say for every point, okay, how do I have to change this so that this works? I simply rotate the entire thing at once by changing the coordinate system. The gears themselves can actually be described in a mathematical way, because you can kind of see that they are spirals that are going outwards here, and the way at which the distance to the center increases can also be described by a mathematical function. So I don't actually have to model each individual point and say, okay, this point is here, this point is there, this point is here. I can simply say, well, there are these triangular things here, and they move in this particular way. Much easier than having to describe each individual one, and then also allows me to print bigger things. Like if I wanted this to continue along here, I can do that very easily by just saying, well, this function that I described, this mathematical function that tells you how to do this, just take this a little bit further. Don't have to say, okay, now take one of these triangles, put it here, then put it there, then put it there. Again, sounds like a lot of work, right? We don't really want to do that. So we use math to make all of that easier. Here's another example. This is a small pyramid that is made up of even smaller pyramids inside. So you can see that there's a kind of the biggest inside pyramid here upside down, and then there's another one up there, and then there are even smaller ones here, and they get tinier and tinier and tinier, and this entire thing forms this pyramid here. Again, something we can describe with mathematical functions. We don't have to say this point here is there, this point here is there for each individual point. We can just give it a mathematical function to describe this. And if I wanted to print this bigger, for example, there would be more tiny pyramids inside there. Okay, and with that, we've had a look at a bunch of different things we can do with coordinate systems, maps, for example, 3D printed models, all kinds of cool stuff. But we've kind of only talked about very small coordinate systems so far. What happens when we have small numbers? This isn't that high, right? Numbers to describe this are not going to be that big. I also want to show you, though, for the end, what happens when these numbers become really big. E.T., cue last video, please.
If you look up an image of the Earth and Moon, you're going to get a picture where they're quite close together, something like that. But in reality, the Earth and Moon are about that far apart. That is the Earth and the Moon to scale. Taking the same concept, but for the solar system, every single picture of the solar system that we ever encounter is not to scale. If you put the orbits to scale on a piece of paper, the planets become microscopic and you won't be able to see them. There is literally not an image that adequately shows you what it actually looks like from out there. The only way to see a scale model of the solar system is to build one.
Welcome to Black Rock Desert. This is Alex. I'm Wiley. He's going to be behind the camera. I'm going to be probably making a lot of mistakes on camera.
We have 36 hours to measure the distances, trace out the orbits, and set up a time-lapse shot from up on top of a nearby mountain. To create a scale model with an Earth only as big as this marble, you need 7 miles of empty space. So that's why we're here.
Why did you guys come?
I don't have a job. At this scale, the sun is 1.5 meters, so about that big around. So we are driving right now to Mercury, and we've arrived. Venus is the same size as Earth. I have the world in my pocket somewhere. And Earth. And this is Mars. Got a couple of robots rolling around on that one. Once the time-lapse is ready, we'll drive each orbit with a light. Hopefully, you'll be able to tell just how big they really are. Onward to the outer planets. Jupiter. Saturn. That tiny light out there is our sun, just over 1 mile away. The sun's way, way out there now. This is it. This is the edge of the solar system.
So right now, it's about 7 a.m. We just woke up right before the sun's about to rise. We are on Earth's orbit. Wiley is over there holding our sun. Cue the dramatic sunrise music.
So if we've made our model correctly, your perspective from where Earth is on the model will match your perspective from standing on real Earth. So if you look back at the sun, you will see that the model sun and the real sun are the exact same size. And that's how you can tell that the proportions are correct. There are 24 people in the entire history of the human species, billions of people, who have actually seen the full circle of the Earth with their own eyes.
Following the breakfast, the astronauts went to the suit room where they donned their spacesuits.
This is man's attempt to get to the moon.
0. We have liftoff. Liftoff at 7:51.
In Earth orbit, the horizon is just slightly curved. When you head on out to the moon, that horizon slowly curves around and upon itself, and all of a sudden you're looking at something that's very strange, but it is very, very familiar.
Oh my God, look at that picture over there. Wow, is that pretty.
You can put your thumb up, and you can hide the Earth behind your thumb. Everything that you have ever known, all behind your thumb.
Not any bigger than that, way up there.
It's really beautiful. You can cry.
That's what I really wanted to try and capture. We are on a marble floating in the middle of nothing. When you sort of come face to face with that, it's staggering.
Thanks, ET. So there you go. You can do really cool stuff with math and coordinate systems, and not limited to 3D printing. Okay, so on Thursday, we're going to have a look at what else we can do with coordinate systems, because it turns out we can do a lot more than just describe points in space, 2D space on a map, or 3D space if we're 3D something. So tune in for that. We'll have a look at some cool stuff, hopefully without the technical difficulties. But as I said, I'm a computer scientist, so every talk I give has to have some. And with that, back to you, ET.
I think maybe you guys can hear me. Yes. This mic stopped working like halfway through. So just kind of like Lars said, of course, the one night we have the computer scientist and the guy that runs the tech school every piece. So no one is immune from that. So Lars, thank you so much. We're going to work on some of these things. We're going to get those videos kind of downloaded. Hopefully you have really enjoyed Mathematics Week Part 1. And again, we will be back Thursday, 6 p.m. here on YouTube Live to finish up Mathematics Week. And then this Friday is the special kind of wrap-up party. So join us this Friday at 6 p.m. That's when we're going to kind of do a big review of the entire WYSTEM program, as well as do a random drawing for the code words and find out who we're going to send this free 3D printer to which school in Wyoming. And so, again, that code word may have shown up tonight. It might show up Thursday, but it's definitely out there. So thank you, everyone. Apologize for the weird little technical difficulties this evening. We're learning as you are through this process of doing live streaming on YouTube. So we're getting better, but there's still a little bit of hiccups here and there. So we will see you back here for the last part 2 of mathematics on Thursday. And then don't forget our wrap-up party this Friday. And then WYSTEM's over, but it's not over. We're going to continue to do a lot of educational videos. So have a great evening, everyone, and we will talk to you soon. Bye.